Section 2.1 is on graphs. So what is a graph? Now, we've talked about how a lot of the techniques we're learning in discrete mathematics help you solve complicated problems. So it's all about learning strategies for problem solving. And when you're faced with a difficult problem in mathematics, it often helps to draw a picture. If the problem involves a discrete collection of interrelated objects, it is natural to sketch the objects and draw lines between them to indicate relationships. This type of sketch is called a graph. Informally, we can think of a graph as a collection of vertices and edges. So the vertices are going to represent the objects in the collection, and the edges represent a relationship between the connected vertices. If those edges have arrows on them, then we call the graph a directed graph. And a graph without arrows is called an undirected graph. So it is important to note that when we draw a graph, it doesn't matter at all where we put the vertices. You can order them however you like, you can space them out as far as you like, you can put them as close together as you want. So it doesn't matter what your overall picture looks like. The thing that matters is whether or not two given vertices are connected by an edge or edges. So there's a lot of terminology associated with graphs and graph theory, so I assume you'll be pausing this video a lot to write down each of these vocab words and what they mean. So we'll start with degree. The degree of a vertex is the number of times an edge touches it. In a directed graph, we can talk about the in degree and the out degree. So the in degree is the number of edges coming into a vertex, and the out degree is the number of edges coming out of a vertex. So let's look at an example. So let's focus in on vertex 4. This graph has 7 vertices represented by these circles, and it's a directed graph because each edge has an arrow pointed on it, giving a direction. So, for example, to read this, I have a relationship from 1 to 2, but I do not have a relationship from 2 to 1 because I don't have an arrow pointing that direction. So focusing in on vertex 4, the in degree of vertex 4 would be 3, since there are 1, 2, 3 edges coming into vertex 4. And the out degree of vertex 4 would also be 3, because I have 1, 2, 3 vertices coming out of vertex 4. And if I were to ignore the arrows and just look at this as a regular undirected graph, the degree of vertex 4 would be 6, since there are 6 edges touching vertex 4. So 3 coming in, 3 going out gives the total degree of this vertex 6. A path in a graph starts at a vertex and follows a sequence of vertex, edge, vertex, edge, vertex, and so on, and the path would end at a vertex. A circuit is a path that starts and ends at the same vertex. So if you follow your path back to where you started, then you have a circuit. An undirected graph is called connected if there is a path connecting any two vertices. So the two vertices don't have to be directly connected, but you should be able to follow a path from every vertex to every other vertex in the graph. And a directed graph is connected if the underlying undirected graph is. So if you look at the directed graph and ignore the arrows, if the underlying undirected graph is connected, then the directed graph will be. An Euler path is a path that uses every edge of the graph exactly once. So you cannot repeat edges. An Euler circuit is a circuit that uses every edge of the graph exactly once. And a good game to play to get better intuition about Euler circuits is the game Single Line. I have linked the game to Canvas under the heading section 2.1. And basically this game has you finding Euler circuits for more and more complicated graphs. So it'll start you off easy. I think level 1 is literally a triangle. So you can start at any vertex and follow the triangle around, and you've made an Euler circuit because you started at a vertex, you used every edge one time and got back to where you started. But as you get through the game, every time you level up, the graph will become more and more complicated. And so it'll be interesting for you to think about which vertex to choose, because not every vertex will work. And we'll talk next week about how we can choose the right vertex. We can mathematically decide which vertex should be appropriate. And it'll make playing this game a lot more easy. But for now, just to help build your intuition, I suggest just playing it a few times. Get yourself to a place where you're stuck, because those first few levels are pretty easy. All right, and then one more technique from section 2.1 are binary search trees. So a binary search tree is an organizational structure that allows one to sort data quickly. So to build a binary search tree, you'll follow these steps. Step 1, start with an item from the list at the top of the tree. You can choose this item arbitrarily, but this item at the top of the tree is called the root node of the tree. The root node will then have at most 2 edges touching it. You can have one child going to the left and one child going to the right. And I'm calling them already, these are called the children of the root node. So you'll start with a vertex and it can have at most 2 lines coming off of it. And we call those lines the children of the root node. Step 3, to place the next item in the tree, you're going to choose an item and compare it to the root node. If the item comes after the root item alphabetically or numerically, it's placed to the right. And if it comes before the root, it is placed to the left. So if you're dealing with words, you'll be thinking alphabetically, and if you're dealing with numbers, you'll be thinking numerically. Then you just want to continue filling in your tree using these 2 conditions. The right child and all of its descendants must come after its parents, and the left child, along with all of its descendants, must come before its parents. So let's look at an example. We want to place the following words, leopard, cobra, shark, horse, alligator, bat, tiger, into a binary search tree. So I've decided to put these in the tree in the order that they're written, but I could, like we said on the previous slide, choose a root node arbitrarily. So I'm choosing leopard to start with. Leopard will be my root node for this binary search tree. And the next word I want to put into the tree is cobra. So I compare cobra to leopard, and I see that C comes before L in the alphabet. So I place cobra to the left of leopard in the tree. Then I look at the word shark. Shark comes after leopard, so I will place it to the right of leopard in the search tree. Now let's think about horse. So I always have to start at the root node. Horse comes before leopard, but after cobra, alphabetically. So I'll have to place it to the left of leopard, but to the right of cobra in the tree. Alligator alphabetically comes before leopard and before cobra. So I'll place alligator to the left of leopard and the left of cobra. Bat. Bat comes before leopard, before cobra, but after alligator. So down the tree, I'll go to the left of leopard, to the left of cobra, and to the right of alligator, and place the word bat there. And finally, tiger. Tiger comes after leopard and after shark alphabetically, so it goes down the right side of the tree, to the right of leopard and to the right of shark. And this picture here on the bottom right is the final iteration of the binary search tree. And basically, it just helps you sort large data sets quickly. So this isn't a very large list. It's it's 7 words long. So that's not very large. But the idea is, if I want to see if, let's say, kangaroo is in this list of animals, I don't have to go through and look at the entire list. I can say kangaroo, JKL. Kangaroo comes before leopard, but after cobra, and after horse, but there's nothing after horse, so I know that kangaroo is not in this list. And I only had to check 3 words to figure that out, as opposed to looking at all 7. When your data sets are quite large, this is very helpful. So we will spend the next week playing with graphs, learning some more techniques about how to interpret their edges and vertices and the degree of the vertices, and we'll have some fun doing so. So please let me know if you have any questions before next class period.